Principles of Bioproduct Separation, Module 12, Crystallization, Segment 3, Batch Crystallization. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about basic concept of crystallization and crystal size distribution. In this segment, we will discuss about batch crystallization. Batch crystallization is the most common method of polishing antibiotics and other biomolecules of moderate molecular weight. Typical batch crystallizers are shown in the figure. These are little more than a stirred tank, which is charged with a warm concentrated solution. The solution is cooled to produce supersaturation. Crystals nucleate, often as the result of seeding, is allowed to grow until it reaches the desired size. Maintaining this growth requires further cooling. Most crystallizations of bioproducts are conducted in this mode because the scale is small, less than 500 kilograms, and the feed is available intermittently. Because these operations are relatively easy in the laboratory and the pilot plant, much empirical information is often available. Once the solubility temperature characteristics of the solute are known and the preliminary conditions selected, a series of experimental crystallizations are conducted, with the initial concentration, the time, and the final temperature are available. The mass of crystals recovered, the product quality, the crystal size distribution, and the crystal's permeability suggest optimum conditions. One of the disadvantages of batch crystallization is that they often give a poor quality, non-uniform product. This is due to the high cooling rates at the beginning of the process. These rates result in the formation of excessive nuclei that cannot grow to the desired size. Such overcooling can also cause precipitation on the cooling surfaces, called as scaling, which reduces the heat transfer in the crystallizer. These disadvantages can be minimized with proper temperature control, often described as a cooling curve, giving the temperature versus time. There are two strategies to predict cooling curve for batch crystallization: population density and empirical approach. To calculate a population density, a balance on the number of crystals of a given size is set up for an unsteady operation in batch, as shown by equation 25. The growth rate is given by equation 26. The nucleation rate, as shown in equation 27, can be used as an initial condition to solve equation 26. Batch crystallization can be analyzed using an empirical approach by assuming a single crystal size and to calculate the temperature required to sustain constant crystal growth. A balance on the amount of supersaturation in the batch unit is as shown in equation 28. Many batch crystallization take place within the metastable zone, where the change in supersaturation is small and nucleation occurs largely by seeding. As a result, the left-hand side and the last term on the right-hand side are both near zero, which results to equation 29. The saturation concentration is a function of temperature, which can be described by equation 30. Temperature profile required to sustain a constant linear growth rate can be determined using equation 31 and equation 32. The scale-up of crystallization requires an estimate of the overall nucleation rate. This nucleation rate is affected by cooling, agitation, and vessel geometry. Secondary nucleation is the dominant factor at a large scale rather than homogeneous or heterogeneous nucleation. Secondary nucleation The generation of nuclei by crystals already present in suspension can occur through crystal-crystal contacts, from crystal wall contacts, and from crystal agitator contacts. Scale up when secondary nucleation is important depends on constant power per volume, constant agitation, constant agitator tip speed, and even the minimum agitator speed to sustain suspension. In the next segment, we will discuss about recrystallization. Until then, I am Yusuf from Institut Teknologi Bandung.